This is the fourth Physics 2212 lab, circuits. So the purpose of this lab is to predict the behavior of circuits containing resistors in series and parallel, use multimeters to measure the actual values of conventional current and potential differences in the circuits, and examine the behavior of ohmic resistors and capacitors. Some background information we'll need to keep in mind are Ohm's law, the loop rule, energy and charge conservation, equivalent resistance in series, and all of the equipment that we used in this lab. As a preview of our results, we found that RC experimental was 10.7 seconds, and we solved for RC true, which has a value of 6 seconds. In part 1 of this experiment, we predicted that I1 equaled I2 from the node rule. This experiment involved two 1.5 volt batteries, two ammeters, two resistors, 47 ohms and 100 ohms respectively. The summation of the resistors gave 147 ohms, and from that point, we could solve for I. We took our 1.5 times 2, so 3 volts, and divided it by 147 to get 0.02 amperes. And we found in this lab that in an open circuit, there's no current and the potential difference stays constant. And here's some of the results that we got. As you can see, our prediction was right, and when you orient the ammeter backwards, the sign flips. So we made a potential versus position graph, and summing up all of our electric potentials gives delta V is 0, which is exactly what we expected. And for round trip potential, V is 0, as we learned. In this part of the experiment, we connected the ammeter with a 100 ohm resistor and found that the current increased to 0.06 amperes. We reasoned that less current is in contact with 100 ohm resistor and resistance decreases, causing the current to increase. And here's a picture of our experimental setup. So part 2 of our experiment involved a 10 ohm bulb, a 20 ohm bulb, a 9 volt battery, and a 200 microfarad capacitor. And connecting the battery to the bulb charged the capacitor, and the bulb progressively got brighter and then progressively got dimmer. And when we disconnected the battery, the capacitor was discharging. And the times that we measured for the discharging of each of these bulbs are 25 seconds and 106 seconds, respectively, for the 10 ohm and the 20 ohm bulb. And so for this part of the lab, we took a video of the discharging capacitor and we read these values of the electric potential from the voltmeter. And we were able to capture the electric potential versus time, which we could then plot and linearize on a graph as shown here. And we found that the experimental RC was the negative reciprocal of the slope of this graph, which gives 10.7411 seconds, and the calculated RC to be the capacitance times the resistance of the setup, giving 6 seconds. So what if you were doing this lab using an ideal simulation and used an ideal simulated ammeter instead of a real ammeter? What's different about a simulated ammeter, and how would it have affected the circuits you hooked it up to? And a real ammeter does not have zero resistance. Therefore, when I connected the ammeter to the resistor in parallel, some of the current went through the resistor. In a virtual experiment, none of the current would have gone through the resistor since the ammeter's resistance would be 0. What if you were simulating this lab and used a simulated battery to charge a simulated capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? And if there was no resistor in the circuit, a simulated model would predict that the capacitor would charge instantly. However, real-life batteries have internal resistance, and as we saw, the capacitor did not charge instantly. Some potential sources of error are human error in simultaneously stopping the stopwatch and discharging the capacitor, and perhaps improper procedure in charging and discharging the capacitor, as it was our first time constructing a circuit. All right, that is all I have for today. Thank you for watching.